Looks good. Okay. Yes, I'm Oliver Eberle. I'm a postdoctoral senior researcher in the Berlin Institute for Learning and Data. So I come from the machine learning side, and through our cooperations with some historians, I got into the field of digital humanities, and I will talk to you today about this process and also generally about interpretability of large language models, but also generally about explainable AI. So the talk is kind of split into two parts. So there's the first part on explainable AI and how we can kind of develop methods and approaches to understand what's going on in these very complex models. And then secondly, also how we can use AI for insights into the sciences, especially in the applications in the humanities. So I'm not sure everyone here is familiar with explainable AI, but I will give a brief introduction about what we, at least in the machine learning community, consider as explanation. So most of machine learning actually has been visual, so it's often based on image data. And only a few years ago, maybe 10 years ago, the field started to kind of get more interested in language. Of course, there's much more work in the past, but the big shifts really is more recent. So in order to understand what like a black box ML model is actually doing, we typically looked at classification models, and you have an input image, there's a certain object on it, and you get a correct prediction in this case. But as a user, you typically have no idea what this classification is based upon. So the whole field of explainable AI kind of like dedicated, probably at this point, like a decade of research to understanding and trace back where these predictions came from. So in this case, you would often get something like a heat map that would tell you which type of pixels were responsible for the prediction. So here, for example, it's kind of visible why the rooster was recognized. But overall, I think it's a broader question why we need explainability. It's to verify our predictions, so to understand that the model is actually doing something reasonable, but also to correct errors and understand how models make mistakes. And it tells us about learning the underlying problem, because models can find surprising solutions, and also more and more to ensure compliance, for example, with the European AI Act. So this used to be the standard, I think, scenario up until maybe, let's say, 5 years ago. So now we are in the age of like Gen AI. And so instead of classification models, our models can all of a sudden do everything. So they can classify, you can ask them for similar images, they can generate new images, you can ask them any question about basically, any topic you're interested in. So now it becomes much more difficult to actually ground a prediction or like an answer of an LLM system into some input. So in the following, I will kind of like lay out a little bit how we can go beyond these heat map representations and maybe consider feature interactions, and maybe also consider more mechanistic perspectives here. So today's foundation models are really multitask and also models of the world. That's why I think many of you are interested in them, because they tell us something about society and like how text evolves over time and like certain features of text. Maybe to recap that the models do really make mistakes, and quite surprising ones. I think there's two well-known examples at this point. One where like a standard object classifier bases its prediction of a boat on like the surrounding water, instead of actually looking at the boat, because it's like a correlated feature, the water, and it's easier to detect because it's texture. And then another one, more recent example of multi-step planning mistakes of LLMs. So here you kind of have the game of the Tower of Hanoi, and you are kind of asked to move the disks from the left to the right. And if you ask the model to predict the next step, it basically directly makes a mistake and moves the largest disk that you cannot access to the very right. So it didn't really understand the physical constraints of the problem. So maybe more recent reasoning models are better at this, but this is, I think on a pretty standard like Llama 3-point-something model. Okay, so now in the second part, I will talk about structured interpretability. So how can we go beyond these type of heat maps? So we already looked at first order explanations, is what we like called them, and then this is useful for explaining classifiers. So you can really get like a heat map over some classification. So here we had like a table classifier, which will become important later on again. So it's historical data, and we were interested in kind of like getting a rough distinction of certain subgroups of data, in this case, historical tables. And we trained a classifier, but we wanted to check if the classifier actually does something meaningful. So here then we checked with heat maps if the predictions are based on meaningful features. And here we could then see that actually the model correctly looks only at the numerical content, which is, I guess, a good proxy to detect that a numerical table in this case. Then we also looked at second order features, so pairwise relationships here became important. So we specifically looked at similarity, and that's how we discovered these. That if you look at like embeddings of two, let's say, images, and you compute a dot product like a similarity score, if you then want to explain the prediction, what we find is that the interaction is an appropriate way of representing this. So we get these kind of like interactions between certain digits here that tell us these two tables are actually identical, and we can verify that our model works as intended. And then in a more recent work, we are now looking at graph structures, and there we find that higher order interactions are actually more meaningful. So here this could be like a citation network or like a network of books or certain entities, and you train them on a classification task, for example. And then we find that like feature subgraphs or like feature walks in this case, so kind of sets of features kind of become relevant together, and we can identify them to get more complex insights into models and also go more towards like a circuit level understanding. So yeah, that's kind of some of our work in interpretability. And now I'll show some examples from language and humanities. So yeah, for first order attributions, we did like a very standard scenario, which is like sentiment predictions, and we trained on movie reviews, which is very common in the language community. And here we then looked at what the predictions were actually based upon. So here we ranked the resulting sentences, computed these type of heat maps using a method that we proposed in the context of transformers. And we find that like what makes a movie review or like a certain review more likely to be recognized as positive are like male Western names like Lee, Barry, Raphael, or the Coen brothers. And like you're more likely to get a negative score if you have like a more foreign sounding name like Saddam or Castro or Chan. So this is kind of like, we found some cases of biases, and I think this is like, yeah, very well known in the community by now. But I think, yeah, explainable AI is very useful to detect these really fine-grained like biases in models. And then also we looked at long-range dependencies. So here, this is like a very standard, I think, LLM scenario. So you have like a very long context window here. So this is like up to 8,000. It's like Wikipedia articles. So you provide the text and you just ask for like a summary here in the end. And then the model gives you kind of like starts generating something, free text. And then what we did is we looked at where this information actually came from, this context. And we were interested in if the models are actually able to use long-range information. And what we found is that the model actually mostly focuses on the later parts of the context. So it really tends to prioritize information that was presented more later in the context. While it can also do like more long-range information and like pull information from there, so from the very beginning of your context, it's much less likely to do so. So this is a log scale, so of counts. So yeah, you should maybe keep this in mind if you kind of like use LLMs to just generate some summary. It's not going to give you a balanced summary of all the text that you presented to it. It will likely focus more on data that was presented closer towards your prompt, let's say. So yeah, so then we also looked at these like second and higher order things. So here, I think in the previous talk, we already discussed embeddings. So here, it's a very standard scenario. So you have a pair of sentences. So a cat I really like, it is a great cat. You just get some embedding out of a model. In this case, it was a bird model or a sentence bird model. And yeah, you produce a similarity score, but you actually don't really know why the similarity has a certain value. So with kind of these like second order explanations, you can kind of get interaction scores between tokens that then tell you why was the model actually considering these to be of high similarity. And here we find, yeah, like it is like a toy example. But like often we do find these like noun matching strategies. So like synonyms or like same nouns are matched. And this is actually is like a large part of like high similarity predictions. And we also like looked at this on like a corpus level. So here we had again a corpus level of review data. And what we found is that the model actually uses a very simplistic strategy to produce high similarity scores. So it's often matches of nouns or like same noun tokens even, noun verbs maybe to some extent, but also like separator and other token interactions. So it's kind of like a bag of token types in a sense. So it's not as maybe intricate or complex as you could imagine. The models are really like, yeah, forced basically to compress a lot of information. And I think while doing so, they then in the end rely on quite simplistic strategies. And I think this is maybe not super obvious or intuitive, but yeah, I thought this is like relevant to know maybe if you want to embed data and like then compute some type of like a ranking between them, that the features that are used to assign a high score may actually be very simple. Yeah, and then we also looked at graph neural networks. So yeah, here you can basically get attributions in terms of walks. So this is kind of like interactions of features. And the interesting thing here is that like graph neural networks, which kind of encode structural information, can also be framed as LLMs, because the attention network basically tells you what tokens can message pass. And with this kind of like setup, we can look at language. So here again, yeah, we have like a token example of like a first order. And there it really doesn't catch the complexity of like language. So it doesn't really get that like, first, I didn't like the boring pictures. It's a negation. So it just gives it a high score because there's like in it. But if you do more complex explanation methods like higher order, you can see that the whole first sentence, which is negative, gets negative score, whereas the second part kind of gets this hierarchy more correctly. Okay, yeah, with this, I will now go to the second part, which is like some insights in the humanities. Like we had a first dip into this with like heat map-based approaches. So here we have a corpus of mathematical instruments, and we were interested in building a classifier that would then give us certain classes, like it's a machine or it's more like a mathematical instrument. And then in cooperation with our historians, like Matteo is here, Mariani, also Jochen Büttner, who's here in the front, we kind of like checked if this kind of like visual definition can help get more like maybe objective criteria. But yeah, you need to really like be close to the domain expert and check if these definitions are actually meaningful. So here we find, for example, that these like fine-grained scales that we have on these mathematical instruments are highly relevant for models to make these decisions. And then like in our largest project, I think that we did in the corporation, we looked at numerical tables, as I already, I think, teased. So here we have like the Sphera corpus, which is like a early modern text from 1472 to 1650. And like, yeah, Matteo and Jochen approached us in the bifold with this type of data. And like at the beginning, I thought it was like extremely unlikely that we can do anything with this. But they were interested in actually matching and finding like an automated way of matching similar semantics of tables, because these could never be analyzed actually at scale. So together with them, we kind of developed like a workflow to kind of aid historians to gain insights at scale. And like one term that came up during this is like the XAI historian. So an historian that can use AI and explainable AI to kind of like make kind of like discover case studies and actually do a more data-driven hypothesis generation. So what actually ends up happening is we built like a type of like statistical model that can give us like bigram representations. So instead of like just throwing the whole table into like a foundation model, which doesn't work because it's out of domain data, we actually trained our own small model, which is able to detect bigrams, and then we can verify that our model works as intended. As here, we can check if like the same bigrams are detected. So here 38 and 38 on two inputs are detected. And so we can actually use this model and trust its decisions. And with this, then we went into like case studies, and here we used cluster entropy to investigate how innovation spread all over Europe at the time. So here we looked at the output of a specific city. So each of these cities, these were like publishing locations. They produced a certain program of types, let's say. So, and some of them were more diverse, and some of them were more focused on reprinting the same things over and over again. But like you could never really analyze this at scale. So we came up with this kind of like clustering approach where you use the representations that we were able to get from our model, compute basically like a distance-based clustering, and then see how many different clusters a certain city was able to produce. And we used entropy to do this. So if a city has really low entropy, it means they keep on reproducing the same contents, whereas a higher entropy score would tell you that it's a more diverse print program. And with that, we identified two interesting cases, for example, in Frankfurt and in Wittenberg. So these had the lowest scores here. And Frankfurt am Main is actually one of the known centers for reprinting editions over and over again. And a more interesting case maybe was Wittenberg, where political control of the Protestant reformers was actually actively limiting the print program, and they were deciding what type of curriculum was to be published. So this was like an historical anomaly that we were able to detect here. And this also matched the historical intuition and the support that they already knew about. Yeah, and I think with this I conclude now. I will skip these like detailed things for now and open for questions. Thank you.
Okay, thank you very much. Wonderful. We have time for questions and comments. Jeffrey, would you like to do a back and forth or?
Yeah, we can start with back and forth maybe. See.
Sorry?
Yeah, we can start with back and forth,
Okay,
I think.
good.
Thank you very much for the talk. Just an observation or question for the entropy focus on publication places, because we have this issue too. Did you guys take into account the fact that sometimes those publication places, at least as listed in the book itself, is not accurate, right? So the author might want to say that because of controversial reasons that it was published in Amsterdam, but it actually wasn't published in Amsterdam, but they put that on the title page. I mean, that sort of historical insight there, is that something you guys took into account when you're looking at cities and cluster innovation? Because we also want to do a big analysis of publication places, but things like this trip us up. Yeah.
Yeah, like I think there's probably a question better answered by the historians, but I think there were indeed places where like they kind of like tried to conceal that they were just like maybe unlawfully copying editions. I think, do we assume that like most of the print locations are correct, Matteo or Jochen? I would guess you've cleaned this by now, but I don't know.
I mean, I have to say that some part of your question didn't hear, because I couldn't hear well from here. But I guess the correct answer is that these works are textbook, university textbooks. So it's a specific genre, academic bookmark in the early modern period. It's not just other kinds of printing in the time. And what we were able to show also in other works is that the major role in deciding the content of these books, now concerning entire Europe, were played by the printers and not by the authors. The authors doesn't have much to say apparently about the content of these books, apart giving suggestions, because they are also lecturers at the university to the local printers. But at the end, it's the printers. But in the case of Wittenberg, for instance, there is this peculiarity that the printers were working at direct commission of from the reformers, from Melanchthon, basically, in this period. And these eventually, so we notice that the homogeneity of the content of these books is extremely high in this place. And this is the hypothesis, is that it was a control, because Melanchthon was controlling the curriculum, while in other places like Venice, Paris, big printers were, more free to decide what to do and what to put on the market. I guess this is the answer, but I didn't get all the point. With the point with Amsterdam, I didn't get that. Sorry.
Okay, thank you. I have Arno and then Malte. We're continuing the back and forth. So Arno is here.
Hi, thank you very much. A very fascinating talk. I have a question concerning the interpretability stuff. Because you're showing that when you do similarity scoring, for example, between text embeddings, that sometimes it's not obvious what the model responds to. And I think this relates to this is a broad question, broad issue for all of us, because all of us are now using these, I used some BERT retriever to get the most relevant documents, and I'm not even thinking about what it means. And also I tried to say that yesterday in my talk, that for sentences, it's not even obvious what similarity means. I mean, for words, it's makes more sense in the pre-training. But what do you think is the lesson for us? Should we always not only check whether our purpose is fulfilled by doing some tests with our data, but maybe we should even look deeper into like this tool, use these type of lenses to see what is the model actually reacting to? Would this be the message?
I think that's part of the message. I think what's key is kind of like to actually really spend the time to get evaluation data. So I think to really evaluate your, let's say, embedding pipeline on something that you know what the correct match should be. Like, I know it's tedious to do. In our case, Jochen spent a lot of time actually like looking at a subset of these historical data and like defining like maybe one or two clusters that we then could evaluate against to see if we actually get the correct rankings from our embedding model. And I think that's kind of the only way how you can do it. And I think alternatively, you can try to get insights from interpretability and see if the features that the models are actually using are the ones that you expect them to use.
Yeah, that's what I thought, because otherwise we might fool ourselves because we think, it works the way we want, but we just don't understand that we have this strange issue in our data that we just don't see when we not look into these lenses.
Yeah, I think what we see a lot of in common foundation models is that they pick certain features that they just like a lot, like maybe like numbers or like certain maybe named entities, and then they activate really strongly if these just randomly appear in two documents, but the semantics of the rest could be kind of different, no? So I think the models are really capable, but getting just like some embedding from some intermediate or final layer, it's very difficult to actually, I think, validate this. So I think doing like either like a training or like fine tuning on your corpus, maybe only on the similarity tasks. So there's like approaches where how you can like train on similarity matchings without actually having to use labels. So like SimCSE is I think a common approach where you just basically fine tune your model without actually having label access to meaningful matching pairs. So you slightly corrupt one of your texts, and then you kind of just train a model to like detect these kind of. So it's a bit like you have two sources. One is slightly corrupted, but they are still the same roughly, and then you train your model on these proxy tasks. So I think that's like one way to maybe pull yourself out of the situation. With like these like semi-supervised, unsupervised, self-supervised approaches. But yeah, I think it's difficult to really ground your insights on models that you don't really understand. And honestly, it's not just that you don't understand, it's also like machine learning researchers don't understand this, and also people at OpenAI don't understand them. So they know how to train them, but they don't understand the algorithms or the underlying processes that actually are implemented by the models. So I think everyone's in the same boat, but I think the companies, for example, have different interests. Now, as long as the user is happy and like it works for their code generation problems and for their like translation issues, I think it's fine. But I think for research, it's a different kind of like challenge. I think we need to kind of understand what's going on, because I think without understanding the mechanisms, what type of insights can we get?
Good. We have two more questions,
Okay.
which we can take if they are not too long.
Yeah, it's already partly answered, but similar direction. So the early work on explainable AI in the image domain, there was this that you go to some of the layers and you see this is the feature that is detected, and then you go to your data and you realize, oh, there's actually like a skewness, like a bias in the data that I put into the training, like this horse and there was this number in the pictures and so on. Yeah. So can we expect similar things from LLMs on corpora, so that you have an explainable AI approach using LLMs that tells you how your corpus is biased? Would you have any ideas of how to do that, or start a research project?
I think that the challenge here is that like the models are trained to detect patterns, kind of, and like a bias is basically just a specific type of pattern. So you kind of, I think, have to define what you consider to be a biased feature or like a biased prediction. Like I think you can do proxies of this. So basically create data sets that you actively maybe introduce biased features into, and then you can see if like there's similar maybe strategies, but like I think it's very explorative. I think it's difficult to find automated, like to find biases in an automated way without defining it beforehand. So I think people mostly use data sets that they define what type of biases they are looking for, like gender bias or certain cultural biases, and then they check if there's like maybe mismatches in classification performance or in the use of features.
Okay, last question, Stefania.
Thank you. Thank you very much for this very great talk and showing, applications, meaningful applications of LLMs. And I think it's only possible with having, interaction between different fields. I was wondering, because we're also interested in applying, graph-based models in order to increase interpretability. And because it came a bit short, and we also can talk afterwards, but could you elaborate on that? And if you think, so what are, the positive sides or the limitations of these approaches?
Yeah. So graph-based approaches are great because you can capture structure in a meaningful way. So you can introduce what type of nodes are allowed to exchange information because you know something about the real world. And I think typical explanation methods have not captured this structure information. So they typically would just maybe highlight certain nodes or certain edges, but not the combination thereof. So I think with these type of approaches that we propose here, you can get more insight into what type of nodes exchange meaningful information. A downside of this is, of course, it's much more complex to compute. It's like, it doesn't scale as well as maybe just computing one type of like heat map over inputs. So this really goes into the model and considers how the information is being processed. And currently, yeah, we're in the process of actually trying to get insights out of these type of approaches in the context of citation networks or like scholarly networks. And yeah, like you do see certain patterns, like maybe you can see like branching of like people that or like communities of people that work together always, or like they always get input from the same type of other circles, and you can get these type of resolution. It hasn't been like super straightforward, I have to say. Like it's very explorative, no, because you don't really know what you're looking for. You know, you just need to kind of like look at the data and see if this is meaningful to your research question. And you need to do a lot of validation. No, like I think with interpretability, a key problem is that it has not always been very robust. So you really need to like use approaches that are actually faithful and really give you the correct and well-grounded explanation method. So I don't know. I think in my experience, it's always a good idea to work together with like experts from machine learning, let's say, because even for us, it's sometimes very difficult to assess if an explanation is actually meaningful, and you need to really verify if like the methods work, because these models are so complex nowadays that there can be a lot of noise and like unreliability if you just use things out of the box, let's say. So yeah, I hope this wasn't too demotivating, but
Oh, thank you.
but yeah, thank you.